Good morning to all. In previous lecture we had seen the proportional allocation is better than simple random sampling without replacement method. In this lecture we will going to see the Neymans allocation is better than proportional allocation. You know the formula for variance of y bar under proportional allocation. So this formula is like this: 1 upon n minus 1 upon n summation I running from 1 to k wi si square. Variance of y bar st under Neymans allocation formula is, if you remember, the formula is 1 upon n summation I running from 1 to k wi si bracket square minus 1 upon capital N summation I running from 1 to k wi si square. We have to prove Neymans allocation is better than proportional allocation. Means we have to prove variance of y bar st under Neymans allocation is less than or equal to variance of y bar st under proportional allocation. Means if we consider this difference, variance of y bar st under proportional allocation minus variance of y bar st under Neymans allocation, then we have to prove this difference greater than or equal to 0. If we prove this difference greater than or equal to 0, this means if we send this in this side, then this will become variance of y bar st under proportional allocation greater than or equal to variance of y bar st under Neymans allocation. And the meaning of this one is Neymans allocation variance is less than proportional allocation variance. This means Neymans allocation is better than proportional allocation. So we have to consider this difference. So proof of this theorem. Remember this formula because we require this formula here. So proof of this theorem. Consider variance of y bar st under proportional allocation minus variance of y bar st under Neymans allocation. Formula for variance of y bar st under proportional allocation is 1 upon n minus 1 upon n summation I running from 1 to k wi si square minus, you know the formula for variance of y bar st under Neymans allocation, put here it is 1 upon n summation I running from 1 to k wi si bracket square minus 1 upon capital N summation I running from 1 to k wi si square. This is equal to now take this summation wi si square inside this bracket. So this will be 1 upon n summation I running from 1 to k wi si square minus 1 upon capital N summation I running from 1 to k wi si square. Take this minus inside the bracket, then this will become minus 1 upon n summation I running from 1 to k wi si bracket square, and this minus minus become plus 1 upon n summation I running from 1 to k wi si square. Now look at this term. Here this term is negative and this same term is positive. So positive negative will get cancelled with each other. And from these two terms we can take 1 upon small n common. So this will be 1 upon small n summation I running from 1 to k wi si square minus summation I running from 1 to k wi si whole bracket square. Alright. Suppose I write this summation wi si as s bar. Then next steps will be like this: 1 upon n summation I running from 1 to k wi si square minus s bar square. Where this s bar means we denote this by s bar, summation wi si, summation I running from 1 to k wi si by s bar. Then I will going to write this next step: summation I running from 1 to k wi into si minus s bar square. So from this term, how this term came, we will going to show this afterwards. But look at here, this term always greater than or equal to 0, because si minus s bar, its square, and this is always greater than or equal to 0. Wi is weight of I strata, so this is again always greater than 0, and 1 upon n also greater than 0. So this whole term will be going to become a greater than or equal to 0. But from this term, how this term came? So we have to show this summation I running from 1 to k wi si square minus s bar square is equal to this one. So I will going to show this by considering this one. I will going to show this is equal to this one. So to prove summation I running from 1 to k wi si square minus s bar square is equal to 1 upon n is common here, same here. So to prove this is equal to summation I running from 1 to k wi into si minus s bar square. So we will going to consider this term, and we will going to prove this is equal to this one. So consider summation I running from 1 to k wi into si minus s bar square. This is just like a minus b square, and you know a minus b square will be a square plus b square minus 2 times ab. So use that formula. So this will be summation I running from 1 to k wi into si square plus s bar square minus 2 times si s bar. Take this summation wi inside this bracket. So this will be summation I running from 1 to k wi si square plus s bar square is constant. So summation will going to apply only for wi. minus 2 times S bar is also constant, and this will be summation I running from 1 to k wi si. We know summation wi always equal to 1. We had seen this in notations. So summation wi always equal to 1, then this will be summation I running from 1 to k wi si square minus plus this will be S bar square into 1, and we denote this summation wi si by S bar. So after putting this as S bar, this will becomes minus 2 times S bar square. Now S bar square minus 2 times S bar square becomes minus S bar square. So this will be summation I running from 1 to k wi si square minus S bar square. So we had started from this one and we had proved this is equal to this one. So this we have to prove summation I running from wi si square minus S bar square as summation wi into si minus S bar square. This means these two terms are same. That's why by using this we had written this as directly this one, and this is greater than or equal to 0. This means variance of y bar st. From this one we can write variance of y bar st under proportional allocation minus variance of y bar st under Neymans allocation. This is greater than or equal to 0. This is greater than or equal to 0. This implies variance of y bar st under proportional allocation is greater than or equal to variance of y bar st under Neymans allocation. And what is the meaning of this one? This means Neymans allocation. This means Neymans allocation is better than proportional allocation. Alright? So we had considered this difference and we had proved this is greater than or equal to 0. And this means this one, and this means Neymans allocation is better than proportional allocation. Now look at this remark. I will going to make one table here under proportional allocation. Under proportional allocation, you know Ni is directly proportional to Ni, and formula for Ni is small n by capital N into capital N. Under Neymans allocation, Ni is directly proportional to NISI, and formula for Ni is NISI upon summation I running from 1 to k NISI into N. Under optimum allocation first or second? Under optimum allocation, we know Ni is directly proportional to NISI upon root of Cn, and in both the cases the formula for Ni is NISI upon root of Ci divided by summation I running from 1 to k ni si upon root of ci into n. Now look at this remark. After writing this formally, look at this remark. Here Neymans allocation becomes proportional allocation if, so when Neymans allocation will become proportional allocation when this Si will be constant. So Si will be constant means S1, S2 up to Sk will be constant. When all these values are constant, suppose A, then this A will come outside this summation and this will get cancelled with this constant A. Then this will become Ni upon summation of Ni. And summation of Ni will be capital N. So this will be small n by capital N into Ni. So Neymans allocation will become proportional allocation if this Si is constant. Alright. Now next question is when optimum allocation will become proportional allocation. So when this optimum allocation will going to become this proportional allocation when Si upon root of Ci is constant. Si upon root of Ci is constant means all these quantities will be constant. So this will be constant, then this will came outside this summation. Suppose this is A, this one is A gets cancelled. This will be Ni upon summation of Ni into N. Summation of Ni is capital N, so this will be small n by capital N upon Ni. So this will become proportional allocation. Next question is when optimum allocation becomes Neymans allocation. When your Ci is constant, suppose Ci is some constant, Ci is suppose some constant A. Then Ci is some constant A means root of Ci will be root of A. This is also constant. So root of A, 1 upon root of A will going to came outside this summation and this will be get cancelled with this 1 upon root A. Because 1 upon root A also is constant. And this the formula of optimum allocation will become the formula for the Neymans allocation. So when Ci is constant, then optimum allocation will going to become a Neymans allocation. Thank you.